Welcome to Next Gen Manufacturing Nexus. Today we are diving headfirst into the world of advanced composites. We're talking about materials that are stronger than steel and, get this, lighter than aluminum. But in this world, there is absolutely zero room for error. Perfection isn't the goal, it's the only option. So let's get into it.
And this right here shows you the stakes. On the left, you've got scrap. Look at that cross-section. It's just riddled with voids and waves, totally useless. But on the right, that's a super material. It's perfectly solid, a single unified structure that's ready for some of the most intense jobs on or off the planet. The difference between these two is forged in a crucible of immense heat and pressure.
So what is it that makes these materials so special? Well, it really boils down to their incredible strength-to-weight ratio. We're talking about stuff that's stronger than steel, but weighs less than aluminum. And that, right there, is why the aerospace industry absolutely loves them for building lighter, more fuel-efficient aircraft. They are, quite literally, the material of the future.
But, and this is a big but, there's a catch. Making these super materials is this incredibly delicate dance between chemistry and physics. One wrong step, just one tiny little deviation in the process, and that amazing super material can turn into worthless scrap before it's even fully formed.
This brings us right to the heart of it all, the autoclave. Now, don't think of it as just an oven. It's way more like a giant high-tech pressure cooker. It's inside this beast that layers of raw material get transformed into one single solid part. This is where all the magic and all the danger really happens.
This diagram really breaks it down nicely. So you've got these layers of composite material, right? They're placed under a vacuum bag. Then the autoclave comes in and applies a crushing amount of atmospheric pressure from the outside, and, this is key, very controlled heat. That combination forces all the resin to flow, saturate the fibers, and cure into one seamless, super strong part.
In a process this complex, with so many things happening at once, the answer is a lot. A whole lot can go wrong. Let's take a look at some of the main culprits that give manufacturing engineers nightmares. First up, erratic heating. Take a look at this cure chart. Each of those colored lines, that's a temperature sensor in a different spot on the part. You see how they're not all rising together nice and neat? That's a huge red flag. It creates what's called a thermal gradient, meaning one area cures faster than another. That builds up a ton of internal stress, which can cause the part to warp or even delaminate, where the layers literally start peeling apart from the inside.
Next up is something even more sinister, porosity. To the naked eye, a part could look absolutely perfect, but then you hit it with an ultrasonic scan, like this one, and it tells a totally different story. All those yellow and green spots? Those are hidden voids, tiny air bubbles trapped deep inside the material. Each one is a microscopic weak point that could lead to a catastrophic failure down the line.
And this flowchart, wow, this shows just how quickly things can spiral out of control. See, a problem like a low cooling rate isn't the real issue. It's a symptom. The real problem might be a choked heat exchanger, which could be caused by something as simple as using low-quality water. It shows how one tiny oversight can set off a chain reaction that completely ruins a multi-million-dollar component.
So, how in the world do you fight back against all this complexity? Well, you can't just slap a bandage on the symptom. You have to become a detective. You've got to hunt down the root cause of the problem to make sure it never, ever happens again.
The main tool for this detective work is something called Root Cause Corrective Action, or RCCA. It's a really structured method they use in everything from aerospace to nuclear power. The whole idea is to just keep asking why, over and over again, digging deeper until you can't ask it anymore. You're not just fixing what's obvious, you're finding what's hidden.
This flowchart is a perfect example of RCCA in action. The problem, the effect, is that heating rate variation we talked about. By working backward, the engineers can pinpoint several possible root causes. Maybe someone mixed different types of parts in the same batch, or the parts were loaded into the autoclave incorrectly. The key takeaway is this: you don't fix this by messing with the temperature. You fix it by correcting the fundamental procedure that caused it in the first place.
So once you understand why things fail, you can finally start to engineer the solution. And it all really comes down to one single concept: mastering the flow of energy into that material.
Think about it like this. On the left, you're just blasting the part with uncontrolled heat. That's what creates all those nasty thermal gradients and stresses we saw earlier. But on the right, you have programmed energy. You're controlling its application with incredible precision. That allows the part to cure slowly, stably, and become unbelievably strong.
Now this is a fantastic way to visualize it. The chart on the left, that's a real super complex industrial cure profile. It looks kind of intimidating, right? But the basic principle is exactly the same as the simple little ramp cure graph on the right. And get this, that simple graph is actually from a paper on dental composites. So whether it's an airplane wing or tooth billing, it's all about gradually increasing the energy over time to get that perfect stress-free cure.
This whole programmed approach really relies on two key things. First, the ramp rate. That's how fast you heat the part. If you go too fast, the outside gets cooked before the inside is even warm. Then you have hold time. That's where you keep the temperature perfectly steady to let all the chemical reactions in the resin finish their job. Nailing this recipe is the absolute key to perfection.
But what if you didn't have to wait until the very end to find out if you messed up? The next frontier in manufacturing is all about preventing defects as they happen. It's about giving engineers a superpower, basically X-ray vision inside the curing part.
And this is a massive, massive shift in thinking. For decades, the process was always make the part and then spend a ton of time and money trying to find any hidden flaws. The new way, which is being pioneered by organizations like NASA, is to actually watch for those flaws as they form and correct the process on the fly.
So here's how this crazy tech works. Engineers actually put ultrasonic sensors inside the autoclave with the part, and throughout the entire cure, these sensors are sending sound waves through the material. By analyzing the signal that bounces back, they can detect those tiny voids, porosity, the very instant they start to appear. It's literally like having a live ultrasound of the part as it's being born. So, what is all of this, the detective work, the precise energy control, the real-time monitoring, what does it all mean for the future of how we make things and for the products we use every day? This quote from NASA's Advanced Composites project really says it all. The ultimate goal isn't just about making one perfect part. It's about making the entire process, from the very first design sketch to the final certified component, faster, cheaper, and just fundamentally more reliable.
And when you achieve that, the payoff is huge. You get way less waste, which is fantastic. You can produce parts much, much faster. The components themselves are just better, they're stronger and more reliable. And all of this gives engineers the confidence to dream bigger, to design more complex and ambitious things that were just too risky or expensive to even try before.
And it all leads to this one final, fascinating question. As we move away from just following a recipe and into a world of truly intelligent manufacturing that can see, analyze, and correct itself in real time, are we getting close to a future where making a bad part is simply impossible?